All right, so this is continuing on with chapter 23 from for the electric potential. We're now done with everything except actually seeing how this stuff works. So I'm making up a problem, and I have not done it before, so this will be interesting. Basically, I want to do something about lightning because lightning is so cool, and it would be pretty neat to be able to make some real ballpark kind of assumptions about lightning. So, this is the problem. Let's say that we've got some clouds here, and we're going to approximate this cumulus cloud right here as an infinite sheet of charge. And we'll approximate the ground also has an infinite sheet of charge. And let's see, what do we, oh, let's say that this is 2,000 meters. So we have some height h, which is 2,000 meters. H equals 2,000 meters. Oops. What else do we want to say? Oh, so a couple things we need to know. Let's assume that a lightning strike will transfer 15 coulombs worth of charge. As a matter of fact, let's go ahead and, even though I drew this as a jagged line, we're going to assume that lightning just goes straight from cloud to earth, okay? We're just trying to get a ballpark idea, and you'll understand. Okay, so 15 coulombs, blah, blah. Okay, the next thing we need to know is the breakdown field for air. By breakdown field, what I mean is, you guys all know that an atom is composed of a heavy nucleus surrounded in some fashion by light electrons, and they're generally neutral, and air is generally an insulator. But if the electric field is strong enough, if I apply an electric field in this direction, that is going to take the negative charges and pull them this way, and the positive charges and push them this way. And at some point, the strength of this field will be enough to actually pull them apart. So one of these negative charges will come flying out. Well, once those negative charges come flying out, is this negative charge free to move? Yes. What does that mean? It means it's now a conductor. And so the point when lightning will occur is when the electric field between the cloud and the ground is strong enough so that it converts air from an insulator to a conductor. And this happens for a field strength of about 3 times 10 to the 6 volts per meter. Okay? So, we now know everything that we need to know. Now, there are reasons why why our calculation is not going to be perfect. But so don't the specifics will not be exact. They will not really represent meteorology, but it's just kind of a fun exercise to see, right? Well, what does happen here? And the question is, how much energy does this lightning bolt strike the earth? Okay. All right, so now, if you want to do this problem on your own, go ahead and stop now and do it on your own, and then you can take a look at the way that I approached it now. Okay, but if you can also watch it and then try to duplicate it, or you can watch it and just not do anything else with it. All right, I'm going to assume that the lightning strike is going to go from negative charges in the cloud and positive charges down here. Once again, it's not the charge that is important, it's the charge difference that's important. So somewhere in here, there's an electric field that's created by charge. For our purposes, I'm just going to assume this is neutral. Oh, we can't assume that's neutral. We have to assume this is positive. Okay. All right. So we'll just leave it at that. All right. So now the question is, what happens? What's this energy going to be? Well, first of all, I know the electric field is going to be 3 times 10 to the 6 volts per meter. For this situation that we described, where we have an infinite charge of negative, an infinite sheet of negative charge, and an infinite sheet of positive charge down here, we know that this electric field will be uniform between them. And so the electric field is uniform, therefore I can go ahead and use our expression that E equals delta V over delta X. Okay, so what do I know here? I know this is what I need my E to be. I know my delta X because that's this H, so I just have, I'm going to call this EB for E breakdown. So my delta V is going to be, E breakdown divided by, excuse me, that's already made a mistake. Where's my, there we go. Delta V is EB times delta X. So what do we have? This EB is 3 times 10 to the 6th volts per meter. My delta X is 2 times 10 to the 3rd meters. So my delta V is 6 times 10 to the 9th volts. I think you'll agree that that's a pretty big number. Looks like 6 billion volts. You probably would not want to be around when there's a 6 billion volt potential difference, which is why you're going to go inside. Okay, so this equals our delta V. And now the question is, how much energy is released? Well, what's the energy of a charge across a potential difference? Remember, this is the potential. The potential energy is Q. I'm going to go ahead, let's do this. We can get rid of all this stuff. Yeah, let's do that. And we already know that, so we can get rid of that. Okay. All right. Okay. So we know that this is our electric potential. We know our charge. This is Q, so we know Q delta V. Now, is it a higher potential energy here or here? Well, this negative charge being far away from here, it has a high potential energy. It wants to be pulled in this direction. It will be going faster when it gets here than when it gets here. If you let it go, it will drop in this direction, right? I mean, in an analogy to a gravitational field. So we know that it's higher potential energy here, lower potential energy here. So what we have, and the reason why that's important is because what we have here is our VB at this point right here where we're going to is actually less than VA. So our delta V is actually less than 0. In other words, it's a negative change. However, it's a negative charge as well. So a negative charge times a negative potential difference is going to give us a positive energy. So now I can just ignore the signs from now on because I figured out what they are. Okay, so all I have is 15 coulombs times 6 times 10 to the 9th volts. And what's that? 15 times 6, 60, 90. So 9 times 10 to the 10th. Okay, so I have 9 times 10 to the 10th joules of energy being released. Just for fun, let's figure out how fast do those electrons need to be moving. Well, I don't actually remember the mass. Oh, yes, I do. I can remember the mass. I'm going to make it up. It's something like, let's see, we have this. We already got, okay. Okay, so here's the point. The point is, we know our change in potential energy. We went from a 9 times 10 to the 9th up here. Oh, yeah, I did something wrong. Our 9 times 10 to the 9th joules, we had a higher potential energy here than we have here. So I don't remember, I don't know exactly what I did wrong back there, but whatever I did wrong, I did something wrong. So the point is this: you have a high potential here, a low potential here, which means you're gaining, you are losing potential energy, but gaining kinetic energy as you move down this height. And so we have 15 coulombs. We have 1.6 times 10 to the minus 19 coulombs per electron, even though electron is not really a unit here. But then we know we have something like, I don't remember exactly, 9 times 10 to the minus 31 kilograms per electron as well. And we know that this energy, 9 times 10 to the 10th joules, is going to equal 1/2 mv final squared. Because they start out right here, stuck in the cloud, and then they zip down here. And the question is, what's their final velocity when they crash in? So we need to put these things together. So how many electrons are in 15 coulombs? I'm going to just round this off to 16. I'm going to call it 16 over 1.6 times 10 to the minus 19th. And this is 10 times 10 to the plus 19. So 10 to the 20th. So we have 10 to the 20th electrons. Sorry, that's just a number of electrons, and each one is, I'm going to call this 10 to the minus 30 kilograms. We'll round that. So each one's 10 to the minus 30. So I have 10 to the 20 times 10 to the minus 30, which gives us 10 to the minus kilograms per electron. And this is just electrons. Again, not a real unit, but it's per electron. So we can cross those things out. And we're going to get 10 to the minus 10 kilograms. And we know that 1/2 mvf squared is equal to our energy right here. Oh, why do we know that? Because the initial kinetic energy was 0. The change in potential energy was 9 times 10 to the 10th. We lost that much potential energy. And again, I apologize for my minus sign there. We lost that much potential energy. And so we know we have to have gained that much kinetic energy. And so what we know is 9 okay, what we know is 9 times 10 to the 10th joules times 2. I'm using now this equation that these two things are equal. Times 2 divided by 10 to the minus 10 kilograms equals V sub F squared. So I'm going to check my units here. Let's see, what do we have? We have Newton sorry, let's do this. My joule is kilogram meters per second squared times meters. So kilogram meters squared per second squared. I'm going to divide by kilograms. So the only thing I'm going to have left is meters squared per second squared. And this is the velocity squared, so the units are right. So everything looks good there. And what do we have? We have 10 to the minus, so we have 1.8 times, oh, I shouldn't have done that in 2 steps. Okay, so this is 9 times 10 to the 20th times 2 means 18 times 10 to the 20th, which means 1.8 times 10 to the 21st meters squared per second squared. Okay, square root of that, what do we got? I don't know what this is. It's something like, let's see, 1.8, so that's about 4.1 times 10 to the 10th? Yes, 4.1 times 10 to the 10th meters per second. Okay, so, does that make sense? Probably not, because what's the speed of light? If I remember correctly, it's 3 times 10 to the 8th meters per second is the speed of light, and so we will not be able to have electrons that are going faster than the speed of light. And so something wasn't quite right with our analysis, and it turns out there's actually an example or a problem in the chapter. I didn't assign it to you, and I actually can't remember what it is. That actually talks about why it is that electrons go in stages. I'm sorry, why electrons in lightning bolts, why the current runs in stages. And it kind of makes sense when you think about it, because remember that electric field, the voltage difference that you need to get is really high. What was that? What did we get? 10 to the 9th? Some like 3 billion electron volts or something? I'm sorry, not electron volts, just volts. 3 billion volts. Well, what if you had a potential difference that was, this minus, and what if you have some plus that's here, that's much closer than the ground? Now, your distance, if this is only 150 meters, well, let's make it easier. If this was only 100 meters instead of 2,000 meters, now your voltage difference only needs to be 1/20th of that. So what generally happens is you have this voltage difference here, you get breakdown to this point, which now moves a whole bunch of negative charges right here, and now they induce a bunch of positive charges right here, and that goes to there, and etc., etc., etc. And this way, instead of having 10 to the 9th, you've got something like 10 to the 7th or something. So that is 10 to the 7th volts. And you have that in stages, but of course, it's very quick. All right, so that was just to play around, and I hope it introduced you to a few of the ideas about how you can apply potential difference, in particular, how you can combine it with conservation of energy to make some calculations. Okay, that's that for that one.